Hi and welcome to this session of Battle of the Cloud Data Warehouses. First of all, remember to explore everything that PaaS has to offer. You have find a lot of free resources online at paas.org, and of course you can also look at things like the PaaS Pro membership and PaaS SQL Saturdays. My name is Johan Ludvig Brattås. I'm a lead solution architect at Capgemini, and when I'm not working, you can either find me volunteering for SQL Saturday Oslo, which I organize. And I also run a membership of a member of the board for the local user group, and I do other various tasks as a volunteer for PaaS. And when I'm not geeking out over tech, you can find me teaching celiacs how to bake gluten-free food. So the agenda for today will be data lakes and data warehouses, so the story behind the cloud battle. Then you have the cloud battleground. We will have a look at the different opponents, and then we will see the outcome of the battle, or do an analysis in the end. So the enterprise data warehouse has been around since 1988. It has evolved over time, of course, both adapting to various methodologies and when new technology comes in and so on, and of course growing of data. It has three main approaches. It's the dimensional approach, which you know from Kimball. Then you have the normalized approach, which is Bill Inman's methodology. And then you have the data vault, or these days it's data vault 2.0. All of them are different, and at least the dimensional approach and the normalized approach tend to be mixed together to make a functional data warehouse. So principles of enterprise data warehouses are, they are subject oriented, so you're looking at single data or subject matters. It is integrated, so you are looking at data from across the organization merged together into a single database where you can query the different sources cohesively. It is time variant, which means that you will be able to look at data evolving over time. And it is non-volatile. So it's, at least preferably, you shouldn't update or delete data in your data warehouse. You will only insert new rows and then do the transformation or the time changes further up into your data warehouse. And of course, we're looking at sums. It is focused on making sums of sales, sums of HR, sums of various sorts. The enterprise data warehouse contains structured schema on write data, and it is relational. And this means that you force your data into tables where you have structured schemas on data types and column names and column lengths and so on. And you store historical data that need to be transformed and organized into one of these methodologies that we've talked about. And typically you transform the data before storing them, or you will transform them first land them into a stage and then store them and then transform them as you move them up into the data warehouse and then further into data marts. And data warehouses are typically very good for business decisions, so both dashboarding and reporting, looking in the mirror to see how things have gone the last few years. And it has a focus on high data quality and exact numbers. You really need to make sure that the sales figures that you're presenting are as they should be, or the financials that you're presenting are exact numbers. This has led to long development life cycles. So people do a lot of testing and quality reassurance to make sure that the numbers are correct before they deliver out, which again means that customers or users have to wait for a longer time to get the data they want. This combined with the data the growing amount of data, so larger data warehouses, put strains on relational databases. And as a response to that, to these problems, we had the data lake. And the data lake gained a foothold around 2011. It answers some pains in the enterprise data warehouse, specifically around the 3 V's of big data. You have 3 or 4 or 5, but I prefer to talk about 3: volume, variety, and velocity. And typical varieties of the data lake are the raw data lake and the business data lake, or you can also call that the layered data lake. And the principles of the business data lake, and this is also of course for the raw data lake, both of them are the same for this first one, and that's land all the information and you land them as is with no modification. For the business data lake, you then encourage line of business to create point solutions. So you invite users into your data lake and start developing or making transformation on the data to find what they want and create a line of business reporting solution. And then you let the line of business decide on the cost and performance of for the problem, removing responsibility from IT and making the business owners also responsible for sizing their data and reporting needs. And means that the IT can concentrate governance on the critical points only, so making sure that the data sources are loaded into the raw layer and then making that available for line of business. And of course also making sure that there is access control on sensitive data and so on. And from a business data lake point of view, you consider the corporate view, so the view for the whole organization, to be just another line of business view where the business needs to go in and create point solutions for the whole organization. And any information is information, so both structured and unstructured is still information. Of course, you shouldn't assume that the lake contains everything, it's just everything that you've gotten hold of so far. So it means you are also able to pull in new data sources when you find that there is something missing. And scale is driven by the demand of the line of business. So you can scale both up and down, and the price is then transferred to the business. So data lake in its basic form is a repository of data that is raw. So you can have blobs, you can have files, images, videos. You can of course also find databases within a data lake. Typically it will be schema on read. So you don't care in what kind of a format it lands in your data lake. That is something you realize or discover when you're querying it later on. And yes, you can have both structured and unstructured data in your data lake. And you want to store all the data that you can here. Raw layer means, again, no transformation, because that will happen later on. And you transform only from raw layers into curated layers. And various use cases and users of have various layers in the data lake. But typically you want to have only advanced analysts or data scientists coming in, as well as data engineers coming into the raw layer, and normal users want to hit the curated layer. And data lakes aren't as good at exact numbers, but they are great for trends and they're great for ad hoc analysis, and that is also what encourages them to have a great speed on a shorter time to market in their development cycles. And the data lake is a great enabler of data science, which can dig around in the raw layer to find the noise or the gold in the noise of the data. And of course also for self-service, that people can just go in and query data wherever they want in the curated zone. The problem, of course, with a data lake is that when you are dealing with the business or the principle of catching everything, you can soon end up with a data swamp if you're not careful. So there's so much data and so much information in your data lake that when users connect to it and try to find things, they can't find anything because it's too much. And if you do not then have proper governance on it, it's hard for people to find out what is there. So to answer these pains, as both data warehouses and data lakes grew in sizes and popularity, the cloud vendors such as Microsoft and AWS launched the Cloud Data Warehouse. And initially this was a response on the challenges faced by traditional relational database management systems, RDBMS. And the answer was having massively parallel processing. So lots of databases distributed across, and then you have processing on each node that the data was across. But it's still a take on enterprise data warehouse. So you're still dealing with the same kind of pains of development cycles, even though the speed of the querying might be bigger, or quicker. It's still the same kind of ETL lifecycle, and you make sure that you have proper data quality and proper results when you sum up. The battleground, of course, is the cloud. And the question is, can the data lake and the enterprise data warehouse merge somehow? Because, face it, enterprise data warehouses in the business has been a sink of a lot of investment, and businesses do not want to just throw away that to make something fully new, or most businesses don't want to. At the same time that they see the value in both having your corporate reporting and your summaries and the strength of the data warehouse, as well as the speed to market and the trends and the ad hoc analysis that the data lake offers. So suggestion for solving these issues was for Gartner launched the logical data warehouse, which means that you still have your close-knit data warehouse and you expand that so you can just connect new data sources into it and offer everything out through a single pane of different semantic models, for instance, or just a single point of contact, and then people can query across the different sources there. And of course you have virtualization, such as TIBCO or Denodo, where you do not do any transformation, you do not do any landing zone or row layer in the data lake. You have a virtualization layer that hits the sources directly, but it is a single point of contact, and then you can just query across. And both of these have logical data warehouse is a bit hard to implement, but we'll see some results that has come out of that. Whereas virtualization tends to have the issue of being as fast as its slowest source. So when you're querying files and Teradata and SQL databases, typically you will still only get the results back at the speed of the file. But this is where the new cloud data warehousing solutions come in. And the opponents that we will be looking at today is, of course, Azure, AWS, Google, and Snowflake. AWS Redshift is first of the opponents, and Redshift is a massive parallel relational database. It is based on PostgreSQL, but just as SQL Server has deviated from its Sybase origins, Redshift is not Postgres. Redshift is a columnar database. So for those of you who are familiar with column store indexing, data is not stored in rows in a table, it's stored in a table with columns and some sort of an indexing where you have row groups and you can query for certain columns in a table, and instead of returning the query engine returning everything and then filtering out, it will just return the columns that you're asking for. Great for compression and can have some nice speed boosts as well. It has distributed databases. So the data is distributed across clusters. And what does that mean? Well, when you are distributing data across databases in the cluster, it means you have a controller node, and then you will be querying, or you will be filling data in several databases and several tables simultaneously. And to make sure that you distribute these, you have various functions, and in Redshift you have 3 different types. You have a partition key, so you can partition your data and say, okay, if you partition by year, then you have one year going to one cluster, or yes, one set of nodes, another year going to another set of nodes, and so on. Then you have all, which means that you say, okay, all the data that is going into this table will go into that data cluster, or all from that one will go into this. And typically you can do a mix match, so all data in a dimensional table should be spread into actually across all nodes, but it will be full copy of each table in each node. And then you have an even distribution where you just randomly select a row into table copy on the different nodes that you have available in your cluster. So we got a copy here. Sorry, yeah, it has 3 versions. It has dense storage, or DS2, which is focused on storage but slower compute power. It's cheapest. Then you have dense compute, DC2, which is then again has SSD disks and strong compute, and it's more expensive. And then you have AQUA Advanced Query Accelerator, or RA3, which is the brand new version, or brand new, it came in, it was announced in January, I think, yeah. Which is then separated compute and storage. So to look closer at DS2 and DC2, you have the same kind of an architecture setup of this. You have your leader node, which is the connection or the controller for all queries coming in to the database. And the leader node will then distribute the query across the different compute nodes within Redshift. So yes, your compute nodes, you can have 1, 2, 3, 4, sorry, yeah, you have 2 and 6 or something. It's but you have several nodes in different scales, and within the node you have compute slices and compute storage combined, and it's in these slices that the querying is going on. And then the leader node will distribute, and if you want to have good query performance, you will typically need to think about how to distribute the data properly so that the queries can hit without having to be gathered from all the different nodes and joined up to the leader node before it's being filtered out again. So typically you want to have the data as close to each other as possible, so it's the query will happen on, or the filtering will happen on the nodes and not on the leader node. It's slightly different from the RA3 version, which has still has a leader node, but then you have compute nodes with its own cache, and then you have your hot data store, and you can dump data that you do not longer need into Amazon Redshift managed disks, because each RA3 version comes with a limited amount of hot table space. But it's something that you can then automate and do within Redshift, how to dump data into cold storage. And managed storage is then, yes, the hot storage is SSDs, and S3 is the cold storage or archive storage. Then Amazon also came up this year with something they called Redshift Spectrum. And Redshift Spectrum is their final approach, or their current approach, on how to merge the data lake and the enterprise data warehouse together. In that you have your traditional Redshift RDBMS, and then underneath there you have a set of compute power that connects to your S3 buckets, and you can query on your data lake as an external table and get your results filtered back up and into your query, as if you're querying against a regular table within Redshift. You also can build materialized views on top of these queries, so that when the users are hitting it, it will function as a regular table, because of course querying against file-based tables will take slightly longer time than doing it within your hot stores and in Redshift. Snowflake is the second contender out tonight, or today, and Snowflake is a cloud data platform. I'll come back to what they mean by that a bit later. It is based on ANSI SQL. It is cloud native, so it's built only as a cloud database, unlike Redshift, which was based on Postgres. And again, it's pure ANSI SQL, familiar SQL. It is also columnar in its approach, and it has separate compute, and they call the compute nodes for for warehouses. And storage is separate from compute, but it is shared among the warehouses. And it is maintenance free, in that you do not need to create any indexes, you do not need to have any DBAs managing the database system. It is done automatically within the Snowflake engine. Of course, even though you do not have to do an indexing here, you still need to think about partition keys and so on. The Snowflake architecture is something like this. So you have the common services, which is authentication, and you are able to integrate the Snowflake authentication and access control with, for instance, Azure Active Directory. And one thing I forgot to mention is that Snowflake is available on all the three different cloud vendors, so you can have it both on Azure, AWS, as well as Google. You have your infrastructure manager, you have your query optimizer, transaction manager, of course, and security, row-level security. You have a separate metadata repository that takes care of all the metadata within the shared storage. You have your compute resources with caches on them, and these virtual warehouses or warehouses are scalable, and you can buy them in different sizes, from extra small to XXXXXL or something. And they scale up and down. And then you have your shared storage, which typically is a set of files that you can load in and then transform so it looks like tables. And it has connectors to the main clouds. And same as with Redshift, you can do querying against external tables, so I'll come back to that as well. Snowflake say that the compute nodes can be seen as a dedicated warehouse per use case. So you have one warehouse dedicated to data science, you have another for finance queries, another for loading data in and transforming data into the virtual warehouse, or sorry, into Snowflake, and then you have one for dashboarding with Click or Tableau, one for dev test and Q&A. And though you have the shared storage with the shared database, you can also, for instance, for your virtual dev environment, you can clone the data that you're developing on. So it's only accessible for a dev environment, and means that even though a developer forgets herself or himself and do a delete from without having a where clause, I think everybody has done that at some time, you won't delete any production data, which is the main part. And it is auto-scalable, which means that you can configure your virtual warehouse to scale from extra small and either stop at large or go all the way up to XXXL if it needs to because of query performance. It also has the ability to auto pause, again something that you can configure. So it can, if it has not been used the last 10 minutes for instance, it can then auto pause or auto shutdown, and that means you do not pay anything for that compute node until it's being queried again and it's hot. And you can also create schedules, so it will typically the finance warehouse shuts down between 12 and 1 because that's when people are taking lunch together, for instance. And as I mentioned, yes, it's very quick data cloning to spin up a dev or test database to develop against. And as I mentioned earlier, Snowflake offers you the ability to query over data lakes. You can have set up file shares towards different cloud vendors, and then that is treated as an external table within Snowflake, and you build your materialized views on top of them if you want to have faster response time for users. So typically, again, enabling self-service on both data lake and relational data in a single development pane, and then you can build a result that will then end up in a materialized view. And that looks something like this. And there's an option also to have a trigger pulling data in as they land in the data lake. They can be pulled in to Snowflake. So back to the question of why Snowflake defines themselves not as a cloud data warehouse, but as a cloud data platform. And it is because not only is Snowflake a relational database or a database that you query against as usual, it supports all the different data that is coming in, both streaming and ETL. You have the data warehouse part. It queries the data lake as an external table. You can build pipelines, what they call snow pipes, to pull data in at a schedule or at triggers such as when a new file arrives. They have a very nice little thing called data exchange or data sharing, which means that you can set up a set of shared databases or shared data that you can either then offer into a data market to sell, to monetize off interesting finds you have, or you can share data with external vendors, third-party suppliers, and so forth. And it also enables data science and data applications. So this is why they define this as a cloud data platform. It doesn't really fit my definition of a data platform, but I see why they coin it that way. Next on is Azure Synapse Analytics, or Synapse among friends. It is also the service formerly known as SQL Data Warehouse. And let's take a look at SQL Data Warehouse first. That is SQL Server done massively parallel processed. And you create it, of course, with T-SQL language, and per default it has column store index turned on. Though last couple of years they also added the option of turning on row-based indexing instead. There are use cases for column store index, and there are use cases for not doing column store index, and it's very nice to have that option. SQL Data Warehouse is also per default separate compute and storage, so you only pay for querying when you're using it, and you can pause it when you're not using it, and that can be scripted. Like Redshift, SQL does distributed databases, and it distributes them by setting up, I think it's per node, SQL node within the cluster. You have your control node, and then you have your storage nodes or compute nodes underneath, and each of these nodes has a set of or copies of SQL database, and then you can distribute the files across, and they are pretty familiar to you if you remember what I said about Redshift. You have your partition key, so for instance year or customer or whatever. Then you have all, and you have round robin. Typically you want to do partition key on fact tables, and you want to have all on your dimensional tables, or also if you're doing staging, because you pull, typically the most effective way of pulling data into SQL Data Warehouse is by pulling in a file as an external table to the Polybase, and then after you land it into a single staging table, you transform it and then distribute it across the nodes from there. And both Redshift and Synapse or SQL Data Warehouse is optimized for star schema models, and this is why you also have to think about how to distribute your tables properly, so that the dimensions and facts are close enough together that they do not have to rely on the controller node in the cluster to filter for you, because the controller node is of course just one single compute node, and you will lose a lot of it. Will be a bottleneck if you start doing it wrong. But Microsoft also sees the issues with having your data warehouse, your data lake. You need to transform the data, you need to do big data analytics on the data, and then you have some machine learning, and you have Power BI, and all these things together is what they then decided to bundle together in one single solution, which is Azure Synapse Analytics, or just Synapse. So Synapse is more than just SQL Data Warehouse. You have your serverless SQL pools. You have Polybase 2.0 for queries against external data sources, and that means you can query Avro, Parquet, CSV, Excel, but also SQL Server, MySQL, Teradata, Oracle, and so on, depending on, of course, what you have available within your cloud system, or within your networking at least. It is also Azure Spark. Logo was for Databricks, but Microsoft created their own containerized Spark distribution. And then of course you also have Azure Data Factory, so you can do your pipeline transformations. And you have Power BI, so you can launch and connect your data sources directly to Power BI within. And all this within one single workspace, which is very handy. It means that you do not have to sit with Data Factory open, Power BI desktop open, as well as Databricks open and SQL Server. Everything is just from one single pane, and you move through different tabs in your development workspace. Google BigQuery is our fourth contender, and Google BigQuery is kind of the special kid in the class. It is serverless, which means that it doesn't care about size of compute nodes or size of storage. It just queries. It is also based on ANSI SQL, so easy language to learn as well, no problem there. It separates compute and storage as mentioned, but it is also columnar based. And since it doesn't care about compute size or so on, it just cares about the query that you're running, and it scales. If the query takes too long, it scales. If it's too much data, it scales. And it scales down again and stops when it's done. You also pay for storage, which is separate. You also pay if you have streaming ingestion, by the way, and that's something it supports. And it is, unlike Redshift and SQL Data Warehouse, which is star schema optimized, BigQuery is optimized for wide tables, so as few joins as possible. Google BigQuery has just recently launched a new feature, which is a multi-cloud version called BigQuery Omni. It is powered by Anthos, so which is their multi-cloud container technology, which means that you can run BigQuery on Amazon or Azure storage and do not have to pay for the egress cost, because the BigQuery engine will be running locally on your Azure or AWS subscription, which is a very interesting take in this battle. I also mentioned, I'm not going to compare Databricks, but I just wanted an honorable mention or a special mention for Databricks Delta Lake, which I haven't used myself yet, but the layout and the architecture and the systems that they have here is very promising. I'm going to take a closer look at that when I have time, and I recommend everybody else who has some time to take a closer look at how they approach this cloud data warehouse, or what they call their data lake house version instead. And that also runs across all the major clouds. So, we've gone through all these systems. Let's have a look at how the battle has gone so far. Well, for functionality, as you probably noticed, all opponents, at least superficially, resemble each other. You query with some kind of a SQL dialect, ANSI SQL, PostgreSQL, kind of T-SQL. And so yes, it is easy to start using it. And you can query against external data on all vendors, but only Synapse, well, BigQuery offers Cloud SQL connection, but only Synapse offers connection to other relational database systems as part of that package. And Redshift Spectrum incurs an extra cost per query, which is something the others do not have pricing for. As for scalability, well, everyone is scalable, but Redshift only offers two different scales. You have, I think they call them large and extra large, but I mean it's still just two ends of, you can only turn it up and down and that's it. And I don't think you can scale it further automatically, but I haven't seen the functionality for RA3 there, but at least for the dense computing and dense storage, there is no automatic scaling up and down. It's you purchase either one or the other, and that's it. And as I mentioned, BigQuery is considered serverless in this setting because it you don't configure any nodes or any minimum and maximum range for it. It just doesn't care. It's you pay for what you use anyway. So for loading data in, all of them support external ETL tools. I mean, Data Factory has a connector to Redshift, it has a connector to BigQuery, it has a connector to Snowflake. You have Matillion, you have Informatica, you have Talend, lots of different ETL tools, and they support them, or vice versa. Redshift and Synapse SQL pools need design decisions on distribution, as mentioned earlier, because of this distributed database system. And that is something that you need to think about when you're loading data in. And BigQuery needs design decisions to avoid the joins, because pricing in BigQuery is based on the amount of data that you push through your compute or your query. And the more joins you have, the more data you pull through. Snowflake do not have these constraints. You load data in or you pull data in, either way. Doesn't matter if you want the star schema or not, even though Snowflake, as the name implies, is star schema or Snowflake schema optimized. That's something that you can build later on if you want. You just pull the files, XML, JSON, Avro, whatever, into the database, and then you can transform it further on from there if you want. Of course, yes, you will have to unwrap XML and JSON to be able to query it properly, but still, yeah. And all tools have a browser-based query tool. So you go to a web page, you log in, you start querying. All of them offer APIs to query against as well, and connectors to things like Power BI, Excel, and so forth. But all in all, Synapse has the richest workspace for full development, from pipeline design all the way to dashboard design within the same tool. Now, Power BI is maybe a little bit of a boast still. It's you have to download a template and open up Power BI desktop, and then publish that before you can do anything else with it. But that's something I hope they fix soon. Synapse is still in preview though, so that is slightly negative. Hopefully they're in public preview, so hopefully they'll launch soon. However, SQL Data Warehouse is now available worldwide, and it has been for a while. And the SQL Data Warehouse now is better off than 2 years ago. You have materialized views, and you have caching. One thing I forgot to put into my slides, but that has to do with concurrency. So BigQuery doesn't care about concurrency, so the number of users hitting it, whereas Redshift and Synapse or SQL Data Warehouse has a maximum number of limit or people hitting it before you have to have a queue. Snowflake doesn't. However, with the query caching mechanism that SQL Data Warehouse introduced last year, people who are hitting the cache do not count as part of the concurrency limit. Snowflake is also available worldwide, but it has fewer data centers per region. And typically this is because there are not a cloud vendor or cloud supplier, so they tend to find spaces or centers per region where all the major cloud providers share or rent the same server space by the same provider, so it's easy for Snowflake to put in their racks and connect them to the different providers. And Redshift is also worldwide, but the RA3 version is so new that it's still not rolled out to all the regions or all data centers within the region right now. And BigQuery is also worldwide within all the Google data centers, as far as I have been able to find at least. Pricing wise, of course, I'm not going to go into full details on prices here, but Redshift has varying prices per version and then per tier, and as well as separate pricing for Spectrum. So there's, even though there are only two price tiers per version, it's still something that you have to keep in mind. And then you have the pricing for Spectrum as an unknown factor within it that as well. Of course, you can calculate that when you know more of your pattern for querying. Snowflake prices storage per gigabyte, and then they have compute per second. That's at least what they are billing, but it is priced according to node size at the compute time. Typically they want you to, or they prefer you, if you do enterprise version, to do a pre-purchase of compute time, and then that scales up and down, and you get a result of how much you have left, or how much is going you have spent so far as part of this. So it's pre-purchased, but you can of course also do pay as you go. But it is scalable, it is auto-posable, and it's, even though it might look expensive up front, you can very much control your cost and usage of the compute that way. Synapse is still in preview, so prices aren't set yet, but the auto scalability up and down on SQL Data Warehouse, your serverless options, and your Spark cluster selections means you also have various parameters that you can set and control to minimize your costs. But of course, since there are so many moving parts, it also makes it slightly harder to calculate upfront what you're going to be spending. And BigQuery prices for storage, streaming inserts, and then it prices on the data that passes through the query. So even though at last year's summit I heard somebody their analyst had been happy they had just run a $50,000 query. The BigQuery pricing scares me a bit, but it might be because I haven't used it enough to understand or predict properly. But again, as long as you think about how you design your tables so that you avoid having too much data unnecessarily pass through your query, it should be fine. And of course, it is very interesting technology to work with as well, in at least for some use cases. So, for my final analysis, my favorite all over is so far Synapse. The flexibility, the combination of various technologies together in one workspace, and the promises of what is coming. Synapse holds a slight lead, but I would say Snowflake is also a very, very good contender. I've been working with both in projects, and Snowflake is amazingly fast, easy to set up, and easy to work with as well. Redshift, I haven't been working with RA3, so I can't speak on that part, but the other versions of Redshift, to me, lacks functionality, and particularly when it comes to just having two different points of the scale. You can't auto scale, you can't pause, and so on. So it's dedicated capacity, and it's both compute and storage, which is a downer for me. But it's popular among a lot of people, and I don't think you can go wrong with any of them, depending on where you are. But I would say if you're not on Azure, look closer at Snowflake if you haven't picked anything yet. And of course, if you're all in on BigQuery or Google, BigQuery is a definite option. If your use cases on querying patterns and data loads fit BigQuery, go for it. But I haven't been using it enough to really fall in love with it. And again, the pricing scares me a bit. But all of these are good contenders, but I would say that Synapse and Snowflake will be the winners. It also, of course, depends on if you do have requirements on country location. For instance, in Scandinavia, where I'm from, Synapse is in Norway, AWS and Redshift and BigQuery are in Sweden, and Snowflake is only in Holland. So for GDPR reasons or for other regulation reasons, look at where the data centers are compared to you, if that fits your use case. So with that, we'll round up with questions, which is a 15-minute Q&A afterwards. And then you have, remember please to put in your session evaluations afterwards. And with that, I thank you for your attendance.